We are looking at chapter number 8, which is gravitation. We'll be discussing the salient points of this gravitation. So every object in the universe attracts every other object with a force, and this force is called the force of gravitation. So gravitation, as we see that there are certain classes of interaction which we found in nature. So gravitation is one of these, and these classes of interaction are gravitational force, electromagnetic force, the strong nuclear force, we also call it as hadronic force, and the weak nuclear forces. Newton's law of gravitation. The force, which is the gravitational force, this is an attraction force, and this acts between two bodies, two masses, m1 and m2, which are separated by a certain distance. We call it as r. So the gravitational force acting between two point objects is proportional to the product of their masses. That is, this force is directly proportional to the product of the two masses which are attracting. This is directly proportional to them and inversely proportional to the square of the radius, or you can say square of the distance between them. This r is the distance between these two particles. In this case, this is mass m1, this is mass m2. So there is a distance of r between them. So F is directly proportional to m1, m2, inversely proportional to the square of radius. When we remove this proportionality sign, then we have this capital G, which is called as the universal gravitational constant. The value of G is 6.67 into 10 to the power minus 11 Newton meter square per kg square. And this will remain, this is a constant, so it will remain same throughout our universe and in our calculations also. This G, gravitational constant, or universal gravitational constant, is independent of the nature and the size of the bodies. Also, the nature of medium between these two. This can be anywhere. This G remains same. The dimensional formula of this G is m minus 1, L 3, and T minus 2. There are certain important points we need to know about the gravitation force. This gravitation force is a central, means if we take Earth, the gravitation always acts towards this center. Also, it is a conservative force. This is the weakest force in nature. If you compare it with the electrostatic force, it is 10 to the power 36 times smaller. It is 10 to the power 18 times smaller than the nuclear force. That is why it is the weakest force. The law of gravitation is applicable to all the bodies. They can have any size, shape, or position. The sun, which we for Earth is the ultimate source of energy. The gravitational force acting between the sun and the planet. This gravitational force is responsible for the orbital motion as it provides the centripetal force. So if this is sun, now the planets we know they are revolving around it. How they are revolving means from where they are getting the energy, from which force. It is the centripetal force, this one. So gravitational pull of the Earth, this is known as the gravity. When we talk about if this planet is Earth, this is sun, then we call it as the gravitational pull of the Earth. Earth, by virtue of its inner mass, it attracts the bodies, and this is known as the gravitational pull. Also, the Newton's third law of motion, this also holds good for the force of gravitation because eventually it is a force. This is going to mean that the gravitational force between two bodies are action-reaction pairs. There are certain points again for the gravitational force, it is independent of the medium between the particles. If you talk about electrostatic force, this force is dependent on the medium between the particles. The gravitational force is conservative in nature and it expresses the force between two point mass because we are talking about some negligible volume. But for external points of this spherical body, the whole mass can be assumed to be concentrated. If you have like this, you can assume it to be concentrated at center of mass. Acceleration due to gravity, small g. We'll come across this g very often in various calculations. So the uniform acceleration produced in a freely falling object due to gravitational pull of the earth is known as acceleration due to gravity. If this is earth, some body is being dropped, then the acceleration of this body or the acceleration which this body feels is the A, which is equivalent to g, that is gravity. We denote it by g and the unit because it is an acceleration. It is meter per second square. It has direction, so it has a vector quantity. It is a vector quantity. It has a direction, and the direction is towards the center of the earth. This value of g is independent of the mass of the object, which is falling freely under gravity. This g changes very slightly from place to place, and for the calculation purposes, we take it somewhere 10 in order to simplify our calculation, but the standard value is 9.8 meter per second square. This value of acceleration due to gravity on the moon is 1/6 of the g of the earth. And if you talk about sun, it is 27 times g gravity on the earth. If you talk about the planets, we know the acceleration due to gravity is minimum on the Mercury. There is a relationship between gravity and acceleration. G is given by gm by r square, and this m is the mass of the earth, which is 6 into 10 to the power 24 kg. This r is the radius of the earth. Generally, we take it as 6400 km, and the value can be taken as 6.38 in terms of meter. 6.38 into 10 to the power 6 meter. The acceleration due to gravity at certain height h means at certain height h from the surface of the earth is given by this gh, g into m by r plus h square. One more expression is there, g 1 minus 2h by r. What are the factors which are going to affect the gravity? First is the shape of earth. See, this g is directly proportional to 1 by r square, as we have known this. Earth is not a proper, you can say, sphere. It is elliptical in shape, and the crust is also not very smooth, the earth crust. So the diameter at poles from this point to this point is 42 kilometers less than the diameter at equator. So if this is x, this is this from this point to this point, it is x minus 42. So when we have less distance, because from the center of earth the distance is less, the g is minimum at equator, but it will be maximum at poles. That means if you take an object, throw from some height, the gravity will be higher at equator as compared to the gravity at pole will be higher as compared to at equator, because the poles are nearer to the center of the earth. The rotation of earth about its own axis. If you take omega as the angular velocity of rotation of earth about its axis, we know that the earth rotates about its axis also. So the acceleration due to gravity at a place having a latitude, say lambda, is given by g dash is g minus r omega square cos square lambda. This is the angle lambda. If you take any point on the earth, like this point, okay, this is also moving. Here we have this central one. We have an axis. So from this point to this point, this is the lambda, this angle we are talking about. So if you take any object here, it has some weight, say mg, and always mg is to the center of the earth. So we have to join these two. This is also lambda, and this is how it is moving with omega. The earth is rotating about its axis. So this is the formula we need to know. When we go to the pole, this angle becomes this one, lambda. Lambda becomes 90 degrees. So we'll put lambda equal to 90 degrees. We get g dash equal to g. So there is no effect of rotation of earth about its axis at poles, because we are talking about the point on the axis itself. But when we come to equator, this lambda becomes 0, because we are talking about this. The object is here. So the angle it is making, lambda, becomes 0. So when we put lambda equal to 0, cos 0 is 1. So g dash will become g minus r omega square. So g is minimum at the equator, and if earth, its rotation about its own axis, g will remain unchanged at poles. But because we see here at poles it is g dash equal to g, but at the equator and from the pole to the equator it is going to change with respect to, because the radius will remain the same, with respect to the r omega square. Omega is the angular velocity by which the earth is rotating about its own axis. Then we have effect of altitude. If we have a body, say here, the h distance, and a body here at h dash distance. So what do you think that which of these body will experience more gravity? The value of g at height h from earth's surface, from this surface, is given by g dash equal to g by 1 plus h by r whole square. So by this scenario, the g increases with the decreasing altitude. That is, g decreases with the altitude. This is going to feel more gravity than this one. Then we have effect of depth. As you know, that the value of g at, say, some depth h, some h from earth's surface, is given by g dash equal to g1 minus h by r. So with this case, the g will decrease with depth from the earth's surface. We are talking about now not at the height, but from here, surface. This is the center of the earth. So if you reach the center, the gravity will become 0. See, put h equal to r here. H and r will become equal. 1 minus 1 is 0. So g into 0 will be 0. So g dash will be 0. So at this point it will be 0. So g will decrease from this point to this point, say from 9.8 to some, say 9.8 is here at the earth crust. At 0, it will decrease till it reaches the center of the earth. Then we have intensity of gravitational field, say at a, this is very important, intensity. We write it as Eg or I. This is the intensity of gravitational field, say at some distance r from a body of mass m. So this gravitational field or intensity is given by g into m. This m capital is the mass of the earth in this case, in this example, divided by the distance of that object from the center of the earth. This is a vector quantity and the direction is towards the center of gravity of the body. So this is the scenario here. The SI unit is Newton meter and the dimensional formula is L T to the power minus 2. The gravitational mass mg, m sub g, is defined by the Newton law of gravitation. Always the mass is computed because we know that this is force equal to mass into gravity. Force, how to find the mass? It will be F by G. This is the kiloweight, that is the weight of the body, and this is the acceleration due to gravity. This is how we compute the gravitational mass. Then we have gravitational potential. So what is the gravitational potential? Gravitational potential at any point in a gravitational field. See, if this is some body, say Earth, it has some gravitational field here. So gravitational potential at any point, so this point, in gravitational field, because it is in the gravitational field, this body is at the gravitational field of the body. This is equal to the work done per unit mass. So work done per unit mass in bringing a very light body from infinity to that point. So it is, say it is at infinity. It is coming at, say, some point in the gravitational field. This is denoted by Vg. Vg is given by W by N, which is eventually minus G into M by R. The SI unit is joule per kg, and it is a scalar quantity. The dimensions are L to the power 3, R to the power minus 2. Here the W is this is the work, and this is negative. That means gravitational potential is always negative. Always negative. This sign shows that. Gravitational potential energy. So now we have seen about the gravitational potential. What is gravitational potential energy? So gravitational potential energy of any object at any point is gravitational field in the gravitational field, because every body has some gravitational pull. Say again, we take the example of Earth. So gravitational potential of any object at any point in the gravitational field is equal to the work done bringing it from infinity to that point, and this is denoted by G. And this gravitational potential energy is given by minus G into capital L, small m by R. This capital M in this case is Earth. This M is the body's mass. Again, we have a negative sign. This shows that the gravitational potential energy decreases with the increase in the distance. The gravitational potential energy at, say, certain height h from the surface of the Earth is given by minus G into capital M small m by R plus h, which is mg capital R by 1 plus h by R. We just have divided them or rearranged them. Satellite. We have man-made satellite, we have natural satellite. So a heavenly object which is revolving around a planet is called a satellite. So if we have sun, we can say that Earth is a satellite. Moon is a satellite of Earth because moon goes around Earth goes around sun. So natural satellites are those heavenly objects which are not man-made. We haven't made them. They revolve around the Earth like this. But artificial satellites are those objects which are man-made and they are launched for certain purpose. Say Earth observation and say some SAR, synthetic aperture radar thing, and various other aspects, say, to communicate. So time period of satellite is given by this expression, 2 pi under root r cube by gn, which is also, you can take like this. If you take g equal to gn by r square, this is 2 pi under root r plus h whole cube by g. And when we talk about near the Earth's surface, what will be the time period of the satellite? It will be 2 pi under root capital R cube by gn. This is given by this expression also, and you can easily find out. We have all these values equal to 2 pi. R is known, gravity is known, so it will be 84 minutes. This P here is the average density of the Earth. Artificial satellites, these are of two types. Geostationary, we also call it as parking satellite. This geostationary means, geo means Earth, stationary means stationary with respect to Earth. So as satellite which always appear to be fixed position at a definite height to an observer on Earth is called geostationary or partly satellite. So if you are here, say this is Earth, you are here and you see a satellite always at this place only. It is not moving. Why it is not moving? Because the Earth rotation about its axis, the time period of Earth rotation is exactly similar to this satellite. So the time this is rotating, this satellite is also rotating or revolving, you can say. This is revolving, Earth is rotating. So the Earth rotation is equal to the revolving time of this satellite. So it is always stationary. It looks stationary to an observer who is standing here. So height of the Earth's surface, the satellite is how much or how far from the Earth's surface? 36,000 kilometers. The radius of the orbit is this much. Time period is 24 hours because, as I said, the Earth is rotating, this is revolving, the time period are same, these are 24 hours. The orbital velocity is 3.1 km per second, the angular velocity is 2 pi by 24, which comes up to this value. And these are the satellites which revolve around the Sun in equatorial orbits. In the equatorial, see, it has to, if this is an equator, then it is revolving around the equatorial orbit. That is why it is stationary. The angular velocity of the satellite is same in magnitude and direction as that of angular velocity of Earth about its own axis, which I told you just now. These satellites are mostly for the communication purpose. For example, if you happen to know about INSAT 2B, INSAT 2C, these are geostationary satellites of India. Polar satellite. Now, as we just saw that the geostationary, they are moving on an equatorial orbit like this. On the equatorial orbit. The polar satellite, on the other hand, if these are the poles, they will move around like this way. So these are those satellites which revolve in the polar orbits, not on the equatorial. See, the polar orbit is that orbit whose angle of inclination with equatorial plane of Earth is 90 degrees. That is, this is the Earth diameter plane, or you can say the equatorial plane. Then this polar orbit, will have inclination of 90 degrees. The height from the Earth's surface in this case, say around 880 kilometers, time period is 84 minutes, orbital velocity in this case is 8 km per second, and this depends on the various satellite. Okay, this is not fixed. If you take some satellite, it may be different. The angular velocity becomes 2 pi by 84, which is this number. We have just converted it into the radian. So these satellites, they revolve around Earth in the polar orbit, or you can say near polar orbit. These satellites are used for various purposes like Earth observation, natural resources observation, forecasting weather, studying the upper region of the atmosphere, say in geometric or GIS mapping. Polar Satellite Launch Vehicle, PSLV. These are the series of vehicles which are launching the satellites, which are polar satellites of India. Then we have orbital velocity. Orbital velocity of a satellite is that minimum. See, this is a minimum velocity required to the satellite into a given orbit around Earth. So some velocity is needed in order for the satellite to orbit around the Earth. So this is the orbital velocity. Orbital velocity of satellite can be given by, this is VO, V sub O, this is orbital velocity, is given by under root Gm by R, where this M is the mass of the planet, R is the, if you have one more relationship, you can use this, capital R by under root G by R plus H. Capital M is the mass of the planet, R is the radius of the planet, and this H is the height of the satellite from planet surface. If satellite is revolving near the Earth's surface, then you can just ignore this H, so it will be R. This small r can be taken as capital R. Now the orbital velocity will become what? It will be, if you see this expression, it is going to be under root g into r only. Okay. So this is going to be 7.92 km per hour because we know the gravity, we know the radius of the Earth. If v is the speed of satellite in its orbit, VO, that is V sub O, is the required orbital velocity to move in the orbit. This is the required orbital velocity, V may be the speed of the satellite. So there is a relationship between this V and VO. If V, that is the speed of the satellite in its orbit, is less than VO, the satellite will move on a parabolic path, and of course the satellite is going to fall back to the Earth. If V equal to V0, the satellite will revolve in circular path or orbit around Earth. So this is the case. But if V is between the VO, that is the orbital velocity, and one more velocity is there, that is the escape velocity, the satellite shall revolve around the Earth in the elliptical orbit. So this depends on both the velocities, where it is going to take the circular path or the elliptical path. Energy of satellite in orbit. What is the total energy? Everywhere we always talk about the kinetic energy and potential energy. So we know by now that the kinetic energy is G capital M small m by 2r. Potential energy always in negative, so G capital M small m by r. When you combine them, you get minus G capital M by 2r. Binding energy. What is the binding energy? The energy which is required to remove a satellite from its orbit around the Earth, or say any planet. We will not talk about Earth again and again. It can be any planet. To infinity. This is called binding energy of the satellite. So if we have Earth, or say any planet, and we have a satellite here, so the energy which is required to remove a satellite from its orbit around that planet to infinity, it can be any place, is called binding energy of the satellite. So binding energy of the satellite of say mass m is given by, see, these two are equal, as opposite in sign, G capital M small m by 2r.
Escape velocity. As the name suggests, to escape, what should be the velocity and what is the velocity? The escape velocity on Earth is the minimum velocity with which a body has to be projected vertically upwards from the Earth's surface so that it just crosses the Earth gravitational field and never returns. This means that Earth is here. Say it has some gravitational field. Now with what minimum velocity, least velocity, a body has to be projected vertically upwards so it crosses this gravitational field and it never returns back. So this escape velocity of any object is given by VE, V sub E, under root 2 G capital M by capital R. This is under root 2 GR, which can be expressed in this expression also. So the escape velocity, it doesn't depend on the mass or shape or size as you see in the expression. Not even because the direction of projection of the body is also not important. So escape velocity at Earth is 11.2 km per second. There are some important escape velocity you must know. For Moon it is 2.3 km per second, Mercury 4.28, Earth, as I said, 11.2 km per second, Jupiter 60 km per second, Sun 618 km per second, neutron star 2 into 10 to the power 5 km per second. So what is the relationship between v escape, that is escape velocity, and orbital velocity? The escape velocity is equal to under root 2 times the VO, that is orbital velocity. So if the velocity of projection is equal to the escape velocity, that is V equal to VE, then the satellite will escape away from the Earth using, or from the planet using a parabolic path. And if velocity of projection of satellite is greater than the escape velocity, that is V is greater than VE, we just have known V when it is equal to VE. When it is greater than VE, then the satellite will escape away following a hyperbolic path. Weightlessness. What is the weightlessness situation? You might have seen the astronauts, they are just floating around. So they are feeling no or less weight. So this is a situation in which the effective weight of a body becomes zero. How this weightlessness is achieved? When you are falling freely under gravity, you are inside a spacecraft or a satellite. If you happen to reach the center of the earth, and when a body is lying in a freely falling lift. Kepler laws of planetary motion. First is the law of orbit. Every planet revolves around the sun in elliptical orbit, and sun is at its one focus. So if I can make it a bigger one, this is an ellipse. Then we have this as the major axis, this as the minor axis. So we have, for ellipse, we have two focus, or foci you can say, one here, one here. Then the first law says, which is the law of orbit, that every planet revolve around the sun in this elliptical orbit when sun S is at one focus. This is known as the perigee or perihelion. This point is known as the apogee or aphelion. The planet is nearest to sun at perigee. It is farthest from sun at apogee. Then the Kepler, another law, which is law of area. The radius vector drawn from the sun to planet, it will sweep equal areas in equal interval of time. This means the aerial velocity of the planet around the sun is constant. Means if at t time it reaches from this point to this point, this is the area. Okay, so the radius vector drawn from the sun to a planet sweeps equal area. If for the time, say same time t, this is the area, then these two have to be equal. This is the law of area. So aerial velocity of a planet, dA by dt, area per unit time in terms of derivative. This is L by 2m, which is constant. L is nothing but the angular momentum and m is the mass of the planet. Law of period. This says that t square is directly proportional to a cube, or you can say r cube. The square of the time period of revolution of planet around the sun is directly proportional to the cube of the semi-major axis of its elliptical orbit. See, in this case, this is the major axis, so this half is the semi-major axis. This whole is B, you can say 2B. This is minor axis, so the half of semi-minor axis, or you can say half of minor axis is semi-minor axis, which is B. So if you consider from this point to this point as 2A, This is the distance we are talking about, A. So T square is directly proportional to AQ. So you can say for T1 time, if it is equal to say K A1Q, for T2 time we have again K A2Q. So if we divide these two, T1 by T2 whole square, this is square, is equal to A1 by A2 whole cube, where A is the semi-major axis of the elliptical orbit. Some important points: a missile is launched with velocity less than the escape velocity. The sum of its kinetic energy and potential energy is negative. The orbital speed of Jupiter is less than the orbital speed of Earth. The bomb explodes on the moon. You cannot hear the sound of the explosion on Earth. You will not be able to hear it. A bottle which is filled with water at 30 degree centigrade and fitted with a cork is now taken to moon. If you open this cork at the surface of the moon, then the water is going to boil. For a satellite orbiting near surface Earth, we have orbital velocity as 8 km per second times 84 minutes approximately. This is approximate. The angular speed is this much, 0.00125 radian per second. The inertial mass is given by force upon acceleration, F by A. The gravitational mass is given by the weight of the body divided by the acceleration due to gravity. They are equal to each other in magnitude. Gravitational mass, this one, of a body is affected by the presence of other body because it is because of the gravitation. This inertial mass of body will remain unaffected by the presence of other body because it remains the same wherever you go in entire universe. Let us summarize. The Newton law of universal gravitation is stating that the gravitational force of attraction between two particles of mass m1 and m2 which are separated by a distance r has the magnitude F equal to g m1 m2 multiplication divided by r square. This g is universal gravitational constant whose value is 6.672 into 10 to the power minus 11 Newton meter square per kg square. If we have to find say a resultant gravitational force which is acting on a particle, say m, due to number of masses m1, m2, mn, so we are going to use the principle of superposition. This F1 to Fn are the individual forces which are acting on this m1, m2, mn, and each will be given by the law of gravitation as you saw here. From the principle of superposition, each force will act independently and will be uninfluenced by other bodies. So what will be the resultant force? It will be given by the vector addition from F1 to Fn, which is given by sigma, that is the summation from 1 to n, all these from m1 to mn forces, summation is Fi. So it goes from 1 to n, Fi. The Kepler's law of planetary motion, these are very important 3 laws, that all planets, they move in elliptical orbit with sun at one of the focal points. So this is the elliptical orbit, this is the sun at one focal point, all are moving like this. The radius vector from the sun to planet sweeps equal areas in Earth at equal time interval. That means from this point to this point, I say from this point to this point, this is t time, this time t time, this moves from this point to this point at t time, this moves from this point to this point at t time, this area will be equal to this area. So this follows from where? From the fact that the force of gravitation on the planet is central. That is why the angular momentum is conserved. The square of the orbital period of a planet is proportional to the cube of the semi-major. If you take from this point to this point as 2a, this will be a. So t square will be directly proportional to the a cube. So the time period t and radius r of circular orbit of a planet about the sun is related by this expression: t square is equal to 4 pi square by g into ms into r cube. This ms is the mass of sun, and most of the planet have nearly circular orbit about the sun. And when we talk about elliptical orbit, this equation is valid if this r is replaced by the semi-major axis, that is r is replaced by a cube. The acceleration due to gravity, there are two scenarios: one above the earth, one below the earth. Say this is d, depth. So this, say at height h, above the earth's surface, this gh is a function, that is gravity is the function of the height, is given by g into me by re plus h. Me is the mass of earth, re is the radius of the earth, h is this height, which is eventually given by, because we can ignore that height if the re, that is radius of earth, which is 6400 kilometer approximately, is very large, then h, you can ignore this. So this equations become g into me by re square into 1 minus r2 into h by re. So gh is equal to g0, that is g, which is a function of h at this point, and at this point, that is at 0 point, this will be equal to 0.1 minus 2h by re, where g0 is simply g into me by re square, because the height is 0. When you talk about coming down or below the earth crust, the depth d below earth surface, now the g, again the function with respect to depth is given by g into me by re square 1 minus d by re, which is like this, is equivalent to g0, that is at 0 depth 1 minus d by re. The gravitational force is a conservative force. That is why the potential energy function can be defined. The gravitational potential energy is associated with two particles m1 and m2, which are separated by r distance, which is given by this relation v. We represent it by v minus g m1 m2 by r. V is taken to be 0 when this r reaches infinity. If it is infinity, this is going to be 0. So the total potential energy of system of particle is what? Is the sum of energy of all pair of particles, and we are taking the pair, where each pair represent a term of the form which is given in this equation. So this prescription follows also from the principle of superposition. If you talk about an isolated system, so if an isolated system consists of, say, particle of mass m, this moving with certain velocity v, in the vicinity or nearby the massive body, say this m, the total mechanical energy of the particle will be given by E equal to half mv square minus g capital M small m by r. This means that the total mechanical energy TME is the sum of kinetic energy, this is kinetic energy, and this is potential energy. So the total energy is a constant of motion. If this m mass moves in a circular orbit of, say, radius a about this mass m, and this mass m is very large as compared to the small m, so the total energy will become E equal to minus G capital M small m by 2a. Now here is a choice of arbitrary constant in the potential energy, as we saw in the previous point. The total energy is negative for any bound system, that is one in which the orbit is closed, that is elliptical orbit. So the kinetic energy and potential energy is given by the kinetic, this is the total energy. Kinetic energy is given by G m capital M small m by 2a. This potential energy is given by G capital M by a. If you combine them, you get this energy only. The escape speed for the surface of the earth, VE escape, is given by 2 into capital G capital mass M of earth, capital RE radius of earth, which is eventually equal to under root 2 G RE. This has a value of 11.2 km per second. If a particle is outside a uniform spherical shell or solid sphere with a spherically symmetrical internal mass distribution, this sphere attracts the particle as though the mass of the sphere or shell is concentrated at the center of the sphere. If a particle inside a uniform spherical shell, the gravitational force on the particle is zero if it is inside here. If the particle is inside a homogeneous solid sphere, the force on the particle acts towards the center of the sphere. So this force is exerted by the spherical mass which is interior to the particle. The geostationary, we have geosynchronous communication. Geostationary satellite, they move in a circular orbit in the equatorial plane. Means if this is Earth, this is the equatorial plane, they move in this plane, equatorial plane, as the approximate distance is around 4.22 into 10 to the power 4 km from the Earth's center. So we have certain physical quantity, the symbols, dimensions, unit and remarks. The gravitational constant given by capital G, the dimension is this much, and the remarks is the value is this much. The gravitational potential represented by V, and which is a function of radius. This is given by minus capital G, capital M, small m by R, and this is a scalar quantity. The gravitational potential is given by minus G, capital M by R, which is a scalar, and because it is this is energy, it is in joules, and this is a potential, so it will be per mass, so joule per kg. The gravitational intensity represented by capital E, or you can say sometimes EG also, is given by G capital M by R square, and we have a unit vector along this direction, so this is vector. So this is the gravitational concepts. Thank you so much. Take care of yourself.